Hi, today we're going to talk about electrons and where they live, in a manner of speaking. To do this, we need to talk about orbitals and quantum numbers. So, quick review of the structure of the atom. So far, we've talked about how in the center of the atom we have a positively charged nucleus made up of protons and neutrons, and this occupies a relatively tiny fraction of the volume of an atom. The rest of the volume of the atom is made up of mostly empty space with some electrons distributed throughout it. Now, why is that the case? In order to understand this, we need to talk about two competing forces acting on electrons. And these are both tied into the electromagnetic force, which acts on charged particles. So the first force that we're going to talk about is an attractive electromagnetic force, because you have a negatively charged electron and a positively charged nucleus, and those are going to be attracted to each other, so the electron is going to be pulled towards the nucleus. Now, if you were trying to stop the electron from moving towards the nucleus, you would actually have to apply force, and so it actually takes energy to move an electron away from the nucleus. So the lowest energy state is for an electron to be as close to the nucleus as possible. However, if you have an atom with more than one electron, and so you have many electrons in close to the nucleus, the electrons will be close to each other. And because they're close to each other and they both have negative charges, they're going to experience repulsive electromagnetic forces that are going to push them away from the nucleus. If you want to keep two electrons close to each other, because they naturally repel, you'll actually have to apply force to keep them close together. And so electrons that are close together are in a very high energy state. So these are our two competing forces. The force that wants to pull all the electrons in close to the nucleus, and the force that is pushing the electrons away from each other, which in some cases pushes them away from the nucleus. So when we think about where electrons are located, basically we need to think of a few principles. First of all, you're going to always want your electrons to be as close to the nucleus as possible, but you also want them to be as far from each other as possible. And the final thing you need to know is that electrons move pretty quickly, so we only know approximately where they are. We can determine probability functions that tell us what areas they're going to be in. I like to liken this to a high energy kid who has just consumed a lot of sugar and has been turned loose in a large room with trampolines. Now, this particular room has trampolines on the floor and also partly up the sides, but just imagine if you had a smaller room with trampolines on floor, walls all the way up to the ceiling, and on the ceiling. So the kid could bounce up and bounce off all sides. As this energetic kid gets going, you can't always just walk into the room and point to where the kid is because the kid is moving so fast. But you can figure out probabilities for where the child is going to be. It's less likely, based on how children ricochet off of trampolines, that they're going to be in the very corners of the room. And also, there's a high probability that they're going to be somewhere close to the center. So we can have the same sort of probability functions applied to electrons. So when we talk about where electrons are, we basically use numbers that tell us an address. So you can think about this in terms of your address. Like if you ask me where I live, depending on where you're from, I'd probably say, I live in Washington, so that's a very large area. And then someone might say, oh, I'm from Washington. Where in Washington are you from? And then I could say, well, I live a little outside Olympia. Well, where outside Olympia? That's where my aunt lives, right? And then I can tell them, the name of the street I live on. And they're like, oh, that's close to my aunt. What number is it? And then I can tell them what number it is, right? So you can see that each of these things narrows down where I live. So our addresses for electrons are four numbers that we call quantum numbers because they're related to energy states of the electron and basically tell us where that particular electron is. The first quantum number we call the n, how far the electron is from the nucleus. When we talk about the number for the n quantum number, we call it the shell. Which shell is it in? Is it shell 1, shell 2, shell 3, etc.? The next quantum number is L. And that tells us what sort of space the electron is in. So there are different sorts of areas within the shell. And again, the shell is a probability of how far away from the nucleus you are. But there's different spots where the electron might be within that shell. Within that type of space, we can then say which specific part of those types of space it's in, and then finally, which direction the electron spins. That seems like a weird thing for an address, but it actually ends up making a big difference for electrons. All right, so let's go through each of those in detail. The principal quantum number n, again, tells us how far the electron is likely to be found from the nucleus. So the higher your n, the farther you are from the nucleus, and therefore the higher energy state you're at. So n equals 1 is relatively close to the nucleus, n equals 2 is further out, n equals 3 is further out, and we have identified atoms where n goes all the way up to 6. The secondary quantum number, we call this a subshell. So the shells are all divided into these different types of spaces. And the further out from the nucleus you go, the more space you have to make these little rooms for electrons to hang out in. And so when you're in that n equals 1 shell, there's only one type of subshell. When you're in the n equals 2, there are 2 different types of subshells, and so forth. The number that's associated with the secondary quantum number L is based on this thing that we call nodes. Well, what is a node? One of the easiest ways to describe this is to talk about a plane, the geometric kind, that cuts through an area where the electron might be. And the more planes that intersect the space, the higher your secondary quantum number will be. So that might sound a little confusing, so let's look at examples. When we have L equals 0, that means you have no nodes. And basically what this looks like is this looks approximately like a sphere. The reason this has 0 will become more clear as we progress through the other sorts of subshells. For now, I also want to say that in addition to numbers, we often refer to these subshells with letters. And so this can be a bit confusing for people. So the S is the sphere. The subshell with L equals 1 we call the P subshell. And I want you to look at these 2 different examples of P subshells, and you'll notice that basically what you have, if you look at the X, Y, and Z axes, which all intersect at the nucleus, you can see that there's a part of the subshell that's on one side of the nucleus, and there's a part of a subshell on the other side of the nucleus, and basically there's a plane that divides these 2 parts. So the P subshell on the left, the plane passes through the Y and Z axes. The P subshell on the right, the plane passes through the Y and X axes. So these are rotated at 90 degrees relative to each other. So you might think of this as, okay, we had this one big blob of stuff in the L equals 0 subshell, and with the L equals 1 subshell, we've basically taken that space and we've chopped it in half. How many times did we chop it in half? Just once. Now, for L equals 2, that means you have 2 nodes. In other words, you've chopped it twice. And so you can see how you've taken that same volume and you've basically cut it 2 different ways. Here you can see the 2 planes, one that goes along the X and Z axes, one that goes along the X and Y axes, and both of those divide this space. So that is L equals 2. And there are multiple ways you can do this. I'm only showing one. I'll show you the others later on. For L equals 3, which we call the F subshell, you are cutting 3 times. And some of these are a lot harder to see the 3 cuts than others. I'd like to direct you to this one, which is probably the easiest to see. You're cutting in a plane along the X and Y axes, the X and Z axes, and then the Y and Z axes. you saw that the more times we cut our space into pieces, the more different possibilities there were to cut it. How many times can you cut something 0 times? Well, there's only one way to, because the one way is to not cut it. When we were talking about the p orbitals, L equals 1, there were 3 ways to do it. You could basically cut it so that the 2 halves are along the x-axis, the 2 halves are along the y-axis, and the 2 halves are along the z-axis. So that gives you 3. Then for D, there's 5. For F, there's 7. And you could imagine how that would keep going up. You'll notice these keep going up by 2. So when you're assigning M sub L values, there's going to be 1 value for each of the different orbitals. What you're going to do is you're going to set up these numbers so that they're centered around 0. So you're always going to have 0. And then they're going to work outwards from that. So in the case of the p orbitals, L equals 1, there are 3 possible orbitals. So one of them is going to be 0, and the others are going to be 1 and -1. So you see how that's symmetrical around 0. For the d orbitals, there's 5 of them. And so there's going to be 0 in the middle, 1 and -1, 2 and -2. For the f orbitals, there's going to be 0 in the middle, there's going to be 1 and -1, there's going to be 2 and -2, and there's going to be 3 and -3. For the s orbital, L equals 0, there is only one of them, and it has to be centered on 0, so it's 0. All right, our final quantum number is the magnetic spin quantum number. We call this m sub s. And basically, this tells us how electrons are attracted to magnetic fields. So if you throw a bunch of electrons into a vacuum, they're just going to go all over the place. But if you throw in a magnetic field with a north pole and a south pole, half of them will be attracted to the north pole and half of them will be attracted to the south pole. This ends up being important because it turns out you can have 2 electrons in each space so long as they aren't attracted to the same magnetic pole. So you can have one that's attracted to the North Pole and one that's attracted to the South Pole. So again, this is a way of figuring out what can go in each space. Now, there are numbers associated with it. A lot of times we just say up spin or down spin with the arrows. You'll see that in the next video. But then we also have numbers associated with it, +1/2 and -1/2. This is a quick summary of the different things that we've talked about. The first quantum number is n. It's the shell, how far out you are from the nucleus. L is the subshell, which is what type of orbital, a p orbital, an s orbital, whatever. M sub L is the specific orbital, which orbital you have within a group. And then M sub s is the magnetic orientation of electrons. So we can predict approximately the location where each electron in an atom will be found. And when you're talking about a specific electron within a specific atom, we use a quantum number to tell us which electron we're talking about. And as we go through and we talk about bonding and so forth, it's really important to know which electrons we're talking about. So we're going to get into that more. We're going to talk about electron configurations up next. In the meantime, I hope this was helpful, and I look forward to seeing you again soon.